uh, we have Engineer Byung Sharma from Aizen Technologies. So he will be delivering a talk on study of fabrication processes, steps, and materials involved for creating a device layer by layer and to find out the characterization flaws of that device using synopsis tools like ETE, TCAD, etc. So he has been working as an application engineering for 2 years in Aizen Technologies Limited. He is a key presenter from Aizen Technologies for TCAD 2. Along with TCAD, he has been trained from Neven Silicon for RTL verifications. He has also experiences as farm engineer for WSN and IoT research. His development by Sensenux. So welcome, Byung Sharma, and I would like to extend special thanks to Agile Technologies for associating in this FDP, and I would like Rashmi to felicitate Engineer Byung Sharma from Agile Technologies. So I would like to request Engineer Byung Sharma to take over.
একটু প্রজেক্টর দিয়ে দিন প্রবলেম হবে slides it anyway.
Hello. Hello. Good afternoon, everyone. Okay, so good afternoon, everyone. Audible properly. So my name is Vyom Sharma, application engineer from ATAL Technologies Private Limited. I'm taking care of TCAD synopsis TCAD tool right now. Right. So, is there someone who already knows TCAD? So you all are first time beginners. So I'll start with the fundamentals and introduction of this CentOS TCAD. So these are the course outlines, as you can see here. First, we will cover the CentOS TCAD overview, which is nothing but the introduction of this TCAD. Then we will go to the different aspects and different tools that are included in this TCAD. TCAD itself is a bundle, complete bundle of multiple tools, right? So we'll then go into different tools that are included in this TCAD bundle list. The first one that we'll learn is CentOS Structure Editor, which is SDE in short. Then we'll see as process in between them, which is also used as a in place of this CentOS Structure Editor. Either you can use as process, either you can use SDE, although they are different in some ways. Right? Then we'll move to the CentOS device, and then at last we'll see CentOS workbench, which is not properly a tool, a technical tool. It is just like Excel. So what is TCAD? TCAD stands for Technology Computer Aided Design. TCAD is a tool which is used to fabricate or model a particular device, not a circuit. It's a device modeling tool, right? So if you want to create a new device of new material or new geometrical structure, planar, non-planar, any FinFET kind of thing, any device modulation that you want to do, except for the unknown material that you will create. That is separate thing. That material you need to create in quantum ATK, which is not included in this TCAD bundle list, right? So that's another thing. Except for that new unknown material, you can create and modulate the material, and you can use in your geometry. You can create your geometry also. You can create your materials also, right? So if you want to have a research on a particular device only, then this tool is best for you, right? Then TCAD consists of mainly two branches, which stands for the process simulation and the device simulation. We will discuss this in the next slide. These are the areas of simulations that we have here. First one is the process simulation. As you all know that a device is actually fabricated in a foundry, right? So in fabrication, during a fabrication of a particular device, foundry has to follow multiple processes to create that particular
geometry of the particular device, right? So those processes, if we need are we can't afford those processes or those researches to enter into foundry, and then we'll do those processes. We'll go through those processes, and then we'll check the result whether it is up to the mark or not, right? So we can't afford that, and it's not feasible actually. So that's why this tool is very helpful in simulating the procedures, the process that we follow to create a particular device. Let's suppose you want to make some changes in the fabrication processes that are usually followed to create a particular device, right? So if you want to make changes in that process, and then you want to simulate it, and then you want to analyze the result whether it is up to the mark, it is up to a research level or not, is it feasible or not, is it practical or not. So that kind of simulations you can do in process simulation. So basically process simulation helps in simulating all the process steps that we use to fabricate a device that may include etching, deposition, ion implantation, thermal annealing, etc. etc. Then we'll come to the next kind of simulation, which is a device simulation. Right? In device simulation, basically you are simulating the optical, thermal, and electrical behavior of your device. Whatever you are creating, you are now analyzing and simulating the optical, thermal, and electrical behavior of your device. That is included in device simulation. These are the application libraries that are provided in TCAT for researchers, for beginners, for users. They can take help from these application libraries. These are already present in TCAT folder. Once you will get this TCAT installed in your system, you will get to know all these libraries, and you can just go through all these libraries so that you can start your project. You can initialize completing things in TCAT. Right. So this consists of CMOS technology, application libraries, then bipolar technologies, application libraries, power devices, heterostructure devices, memory devices, and optoelectronic devices. These are some. There are some others also. Obviously, no single person can have a knowledge of all these application libraries. Okay. So whatever your project, whatever your interest is, you can just opt accordingly. From here, the actual process of TCAT starts. These are the basic tools that are included in TCAT. The first one is SDE, then the second one is S process, then the third one is S device. These are the three tools that we need to invoke actually. That's why these are main tools. Otherwise, there are so many other tools that work in background or auto call function, or we can call it manually also, right? So the first basic tool that is in TCAT is to create a structure. When you start modeling your device, the very first thing is the geometry of the device, right? So to create a geometry of your device, there are two tools that are available in TCAT bundle list, which are responsible for modeling the structure or geometry of your device. The first one is SDE, which stands for Centaurus Structure Editor. Although the abbreviation says SDE, it doesn't match Centaurus Structure Editor, but it is SDE, right? Then comes S process that I already told you. SDE and S process both may or may not replace each other in some ways. But in SDE, basically, we are just dealing with the geometry mainly, right? But in case of S process, we deal with geometry along with the processes itself, right? So you can in some way say that S process is the larger option or the wider option of SDE. Then we have another tool which is responsible for device simulation. The name of the tool is S device. Right, the structure one, that SDE one, is the only tool which is available in GUI mode, right? Because it deals with fabrication of creation of your geometry and modeling of a device, right? That's why SDE's tool is available in GUI. Wherever S process and S device is not available GUI mode. So you need to code accordingly and then start simulation. Then you will get those graphs, plots, band diagrams, and other properties of a device, right? So that third one is as device. Now the fourth one that we look here is as visual. As visual and as impact. Both the tools are responsible for analyzing what we have created already, right? So whatever we have created in the geometry, whatever kind of doping we have added, whatever the process that device has gone through, and whatever the electrical behavior changes or optical or any other behavioral changes that we have done in as device, those if we want to analyze, ultimately we need to get some results from that one. So as visual is helpful in getting those results. So inspect is now outdated. So now everyone is using as visual. The inspect was same as visual. As visual is updated one of inspect. So this is the overview of TCAD tool. First we have CentOS structure editor SDE tool along with the CentOS process. It's not always mandatory that you use as process along with SDE. If you are modeling your device, you're creating a geometry of your device in SD, you can directly go to S device in the next step, right? Wherever also you can do SDE, you can use SDE for modeling the device, then go to S process for adding the different kind of processes involved in that fabrication, and then you can switch to CentOS device. Ultimately, the motive is CentOS device is must, and CentOS structure editor is must, right? So this was the basic flowchart of this. Then from here, the first tool starts CentOS structure editor SDE. It is available in 2D and 3D, both ways. That's why the TCAD bundle is once you start. If you want to purchase that TCAD, that salesperson will ask for whether you want to purchase it in 2D mode or in 3D mode, right? So it is available in both the modes, 2D and 3D. Okay. Also, it is available in GUI that I already told you. Along with the GUI, when we start drawing or start creating the geometry of your device, there's a blank space downside there, which automatically prints the commands associated with that steps that we are following in GUI, right? That we'll see later. So that command we call it as script language command, right? You can directly write it if you have knowledge of that scheme language. These are the steps that we will follow when we start using the SDE tool. The very first thing is we'll create a region, then we'll go to the exact coordinate mode. We'll do that by this tool after a few minutes. Then we'll select a material, a different kind of materials for different kind of layers or different kind of processes, right? Then we'll go to the rounding edges, which is optional. If your geometry doesn't need rounding edges, then no need to go to this step. Then we'll define the context of a geometry, and then ultimately we'll add doping to the material, and then we'll go to meshing. These are the basic and necessary ones, right? There could be others also. This is how the GUI window of SDE looks like. When I'll open the tool, this is how it should look like. Empty plane where you will draw your geometry, and at the downside you can see some codes are automatically printed, right? So whatever the movement or whatever the step you do in that empty plane by your mouse directly, that automatically get printed in this script language code. This is a screenshot of 2D device structure of NMOS. this is how it looks like when we start doing these things. So I have taken a screenshot and edit just to make you a look at how it looks like when we start creating a device. This is how a 3D device looks like in this plane. In fact, right. Now this is how we open STE in GUI mode. So this one is the command that we need to enter in our terminal to open this STE2, right? Now TCAD is only available for platform like CentOS 7 or 8 or RHL 7 or 8, which are Linux based operating systems. It doesn't work in Windows or Ubuntu, right? So that's why you can open the command terminal anywhere that I will show you, and then you need to enter the command SDE space hyphen no open capital G to open this in GUI mode, right? These are the steps that we'll follow to create a geometry again. To create a region, we'll follow these steps. If you want to create a rectangular region, then we'll go to the draw, then we'll go to a 2D region. Since I have selected this 2D region, that means that I am working in 2D mode, right? That's why it is rectangle, otherwise it will be cuboid. So we'll go to draw, then we'll create 2D region, and then there we'll select a rectangle. Then click and drag a rectangle to create a polygon. That's it. The second thing that we'll do is exact coordinate mode. Exact coordinate mode is basically, as the name suggests, that the coordinate, you are dealing in coordinates right now. In the very first step, if we'll take a rectangle and we'll select the material, then the cursor will come to that empty plane. If we drag a cursor, then the rectangle will get created automatically. But what will be the size of that rectangle? We don't know. Although if we know, then we can't judge by dragging a rectangle that it is about that much size that we want, right? To prevent this problem, the solution is exact coordinate mode. We'll deal with the geometry in terms of coordinates, right? X, Y, and Z plane. If you are working in 3D, and if you are working in 2D, then X and Y plane, right? So that coordinate we'll mark. So before starting modeling the device or creating the geometry, we'll take a paper and pen. We'll draw by our hand our geometry. We'll take references of the coordinates of X and Y, that which coordinate is which one, and which point is pointing to which coordinate. Accordingly, we'll start from there. Then, right? So if we turn on that exact coordinate mode, then in that case, once we drag that rectangle on the empty plane, this time it will not create a rectangle, but it will open this window that you can see at the right side. Since it is in 2D mode, it is asking for X coordinate and Y coordinate, not Z coordinate, right? So from which X-axis point to which axis point, and from which Y point to which Y point, this is how it will create the rectangle, right? In exact values, exact dimensions. This is how you will select a particular material that will be used in your geometry or for a particular region or particular layer. Layer by layer, you can differentiate the materials one by one. You can keep on changing the materials also, right? So since it is a screenshot of that material list, so it is just 20% of that complete list. I'll show you the complete list when we start using this. So this is how you can select the material. Just drag and select the desired material. This is optional feature, rounding edges. If you want to round the edges of your geometry, then you can use this fillet option, right? Edit 2D fillet and then enter, and fillet option. Fillet radius you need to enter and then enter. Then we'll go to the next step is defining the context. Now the basic structure of our geometry is prepared. Now we are adding the contacts at different point wherever you want to do that, right? So to do that, we'll go to this step, defining the contacts. First, we need to define the contacts. Accordingly, we'll define the contacts there. We'll give them name, right? And we can change the color that it will indicate. Let's suppose source and drain. Source is green, showing green by green color. Drain is showing by red color. So that we can change from this option, right? We can change the thickness of that mark that it will show, like, to indicate that this one is drain, this one is source, right? So these kind of modulations we can do from here. Also, we can change the pattern, because ultimately when we look at that geometry, it will be showing multiple colors and multiple this checks and all kind of designs, right? So accordingly, according to design, then it will be helpful for us to judge that this one is drain, this one is source, right? So it is just for that purpose. So now we have defined the contact, and thereafter we will define a region as a contact. If a region is a contact, then we need to follow this particular step. Once we have defined the contact, we can start adding the contacts also, right? If you have defined a particular area, then you can start adding that contact also. If you have defined the area, then you can add this, what we call it, contacts, right? This is the window that shows how we can add the doping profile. Now doping profile is of two kinds. Now, first one is constant doping profile. Let's say if your device completely has a linear and uniform kind of doping, then we'll go to this constant doping profile. Otherwise, we go to analytical doping profile, right? Which is this one, analytical doping profile. Doping changes according to depth or left right movement or up down. Anyways. Now defining the mesh strategy. Mesh is what? Ultimately you are breaking, or you can say you are creating a mesh just to break your device into finite number of pieces, where you can apply the physics at each and every part of your device, right? So whatever the model you will be using, that model need to be implemented on each part of your device. That will be taken care by this particular mesh only, right? So that matching could be of denser matching, rear matching, that will. This is how we'll save the model. Just click on the save, and these files will get created. The geometry that you have created will be saved in .set format. File name with the extension .set, right? So if you want to reopen that file, you can just go to that folder. First you need to open that SD. From there you need to go to that folder, select that .set file, and it will reopen. Whatever you have created will get reopened in that SD mode, right? So the first file was file name .set. Then the second file is scheme language, scheme file, right? Whatever we were creating in GUI manually will get created automatically in codes. That's what we call scheme language command, right? Yeah, scheme language codes. So the extension for those scheme language codes is .scm. So you'll find .scm scheme command extension right there. Then the third file that will be created is file name underscore msh, which shows meshing .cmd command, right? So this file contains all the information related to mesh and topics, right? Also, TDR file is get created that contains all the behavioral and geometrical identities of the device that contains it, that is contained in .TDR file. Boundary conditions also. Now the last geometry and you think that it looks fine and you are done, then ultimately to get the results, to get implementing the mesh and the physics into that part, into that device, the last option that you need to click is build mesh. Once you click on build mesh, it starts simulating and then it auto calls the as visual so that you can open the geometrical profile, the geometry that you have created. It will be opened in as visual. Once you click on this build mesh, it will auto call that as visual. You don't need to call as visual separately. So and as device processes of that as device steps of that as device ends there, right? Now the mesh tool comes, Centaurus mesh, which is again not a tool that we intentionally call from the terminal. It is again auto call function. When we click on this build mesh do two things. First, build mesh needs to be implemented first itself. So that implementation was done by Centaurus mesh. Yeah, S mesh we can call it, right? And once the mesh is implemented, the physics is applied on that particular device. To get the result, it will auto call to S visual to see the result, right? So these two things happen when you click on that build mesh. So Centaurus mesh is that tool which is related to that meshing. So it can have three kind of meshings that are given here. Axis aligned mesh generator is there, offsetting mesh generator is there, tensor product mesh generator is there. It is not that important, but you need to get these names at least. So this is the difference between these three kind of mesh engines that we use. Axis aligned mesh generator can produce the high quality mesh for non-planar structures. Offsetting mesh generator can produce the 2D and 3D layered mesh at device interfaces, right? And then the tensor product mesh, we use that for EM layer solving calculation, right? And this is how that mesh looks like. If you look at that meshings in 2D, it looks like triangular grids, right? And that triangle becomes tetrahedral when it comes to when the device is created in 3D mode, right? So that is shown in this picture. That's how we create a tensor product mesh generator. Finite breaking of this into device into grids, right? Then comes the last tool that we will be using here as device, right? As I told you, as device is responsible for simulating the electrical, thermal, and optical behavior of your device. It is not available in GUI mode, right? So if you want to call that manually from the terminal directly, then what you need to do is the first thing is that you must have the code file of this as device, right? And then if you want to open that as device, or you can say you want to simulate that file, whatever you have created, then the command will be as device space that file name and enter, right? Now there are so many flags which provide different features of this as device, which is not a part of fundamental, right? Once you start using these things, then you will get to know those flags. -p you can additionally add, -f you can additionally use, right? So those are kind of shortcut you can say. But ultimately the main the main thing that you write to open this tool is as device and then space that file name, right? That file name will be the code that you have created for this as device, right? Otherwise you can call this particular tool, you can add this particular tool in SWB that I'll show you. SWB, this is the flow of inputs and outputs in as device. Now as device needs 2-3 things basically as an input, then it will produce some output for you. The first thing that Centaurus device needs is the geometry. Now where we have created geometry, either we have created it through Then the another file that CentOS device needs is the command file. Obviously, the command file is basically the code file that you will you will create to run this CentOS device, right? Actually, this is the main file which we say that it is a file of CentOS device, input file of CentOS device. The rest of the inputs are being created as an output of from other tools, right? But this file is a raw file that we generate, we code manually. Description.cmd only, command file. Along with that, there's an additional file that is not mandatory actually, but you can use or may not use that file, which is parameter file. But 90% chances is that if you are going into a research, then you will need that parameter file, because if you are using this tool for a research, then you will in some way will make some changes in some material, you will deal with some material differences, right? To deal with those materials or the parameters of that particular material, you must know how to deal with this parameter file, right? So parameter file actually contains the parameters defined of a particular material. So all the material list that I was showing you in that screenshot, and I'll show you also the complete list. All the materials that are present there will have a parameter file associated with that contained in material DB folder. That also I'll show you. Right? So the third file that CentOS device needs is parameter file. Dash means description, underscore dash means description, then SI is for silicon. Since this example is for silicon, so it has taken silicon parameter file, otherwise it could be anything else. So ultimately, the name of the file becomes underscore dash, then the name of that material dot par, right? Dot par stands for parameter file. So these are the three files that CentOS device needs as an input to start running. Once we once we provide these inputs to the CentOS device, then we can start CentOS device, and the CentOS device will start simulating the device, and accordingly it will produce results. Whatever you have coded in that description.cmd, accordingly it will produce result, right? That depends on multiple things. What kind of material you have used, what kind of code you have written, what kind of models you have taken care, right? Added into that code, and what kind of physics you are taking care, right? And what kind of math solver you are using. So we'll discuss all these things when we go into that as device. So the three inputs that this as device will produce is, the first file is current underscore description.plt. Wherever you see that .plt, that means this file is important in terms of this plot. It contains actually plot, right? The curves that you expect from your device to generate. Those curves are actually into this plt file, .plt file, right? The second file that is generated by this CentOS structure, CentOS devices, description.tdr. Don't go into that plot part written there, it is wrong. So description.tdr, tdr contains again the other information related to matching, related to boundary conditions, related to initial biasings, all these kind of conditions, and related to geometrical structure also. That file that information is contained in .tdr format, .tdr file, right? So that will be the output of CentOS device. Along with those two files, we'll always get that log file. Log file we all know it is to check the runtime status. Then these are the command. These are the points that we actually take into account when start coding with CentOS device. So these are the main sections that are included in CentOS device code, right? The file section, the electrode section, the physics section, the plot section, math section, and solve section. We'll go into details when we start using that as device. What we can solve in this as device physics. right? So these are the list of as device physics. Please have a look at these points. Most common uses these mobility models, tunneling, organic devices are now trending.
This optical generation radiation models, what type of models are you generating?
Who is asking? Sorry.
Optical generation radiation models. On right hand side, point number 4.
Right, right.
इसमें what type of models are we looking?
That actually I don't know. That you can go and check that manual. There's a manual of around 1200 pages, right? So you can go through that whole manual. You can just search with your topic and you will get the related information there. Right, right. Without using that manual, without taking that reference of that manual, you can complete it.
There's so many.
Right, right, right. Then comes the mobility model. These are the list of some mobility models attached here in this presentation. Keep a look at these models. Phonon scattering mobility degradation, doping dependence mobility degradation, carrier scattering mobility degradation, interface mobility degradation, and high electric field mobility degradation. Right? Whichever the mobility model suits you or project suits you, you can opt that. These are the other list of mobility models. These are. It happens many a time that you itself don't know that what kind of physics, what kind of model you need to use, you should use in your project for to get that particular thing done, right? So accordingly, you can take help of again that manual. Once you start searching in the manual, your content, your keywords, then you will get multiple information, and then you will get some idea that which model is actually suitable for your project and which model is actually related to your target, your achievement. And once you will get the name of that model, if you want to add that model, again you need to switch to that manual to get that syntax.
So is there a free available
Manual is free.
For students, if we want to use it, just a MATLAB
Tool.
there are some
No,
online
tool is not. Tool is not free. Tool is paid. Actually, this company has not segregated academic and research separately. Right? That's here closest to this college it is available in IIT Guwahati. Now generation and recombination models are there. These are the names of these GNR models. Please take a look. These are the points that we need to consider when we are dealing with parameter file, right? When we'll enter into the parameter file, these are the points that we must know before we switch to that parameter file, because ultimately we need to make these points changed. It's not always mandatory that you need to change, but these are the main points that you need to know about a particular material, because ultimately material is a parameter file, right? So epsilon you must know, the lattice heat capacity you must know, thermal conductivity, that accordingly changes demand to demand, right? Refractive index could be there also. This is how we add parameter file in the project, that we will see when we start. And this is how Centaurus workbench looks like. SWB is the abbreviation of Centaurus Workbench. Centaurus Workbench itself is not a technical tool. It is just a tool which makes other tools running at a common environment, make it user friendly to operate all the tools handy, right? So it is just a tabular kind of tool which helps to run multiple tools together. So you can easily use that. It make it user friendly. Okay, then thank you. Slide is over. Now we see. Before starting, you must know a few things about the tool installation. Once the installation of the TCAD is done, you will get this folder, synopsis. You will enter and you will find out this Centaurus folder in your system, right? So we'll enter into the Centaurus system. Here you will find two different folders. First one is STDB, and then another one is the name of the version, whatever the version you have installed of TCAD will be named here, right? So STDB is an intentionally created folder where all your projects that you will be running will be saved, right? And when we enter into this folder, you will get these multiple folders, right? So we don't have to deal with any of the folder, just with TCAD. Into TCAD we have current or version name again. Then we enter into the current, and here we will find our things, right? The first thing is application library. I showed you in a slide that we have multiple application libraries related to a project. So these are the application libraries. You can start learning from these libraries if you don't know how to use that particular tool, right? So advanced transport, analog, backend, bipolar, CMOS, FinFET, hetero, then memory, then optical, then power, multiple application libraries are there. Then comes calibration library. Obviously, once you start using the tool, you will find out that sometimes you need calibration in this tool. So that library is provided for that purpose. Doc contains some additional documents. Lib contains all the library information of the tools and the materials also, right? So once you will enter into this lib, you will find a folder called as device. Where is it? As device. As device. Once you will enter into this as device folder, you will find out material DB, material database basically, right? So according to the versions changed in TCAD, these are the list of the versions year wise, right? So if you don't enter into these, also you will get these materials, right? So you can have a look at the list of materials that are available here. So these are .par file. As I told you that any material, if it is present in TCAD, that will have .par file. Means all the parameter of that material is written into these files, right? So if you want to add any material into your project, then you will have to deal with this par file, right? This is the list. If you want, you can just open any of them. It looks like this. Here you will find multiple parameters, right? Epsilon for permittivity, then lattice heat capacity, then kappa, and then band gap, refractive index. All these kind of parameters are defined here of that particular material. So if you want to add your own material, then it is always helpful that you choose the material whose properties are closest to your material, desired material, right? And take a copy of that particular material, make changes into that material file and make it your own file. Okay, so now we can start with that SDE. Now to open that first tool, SDE, to create a geometry, the very first thing that you should do is you create a geometry on a paper with your pen, mark the coordinates, and just note down those coordinates. Accordingly, you will start that SDE. Right? So I'm starting this SDE with this terminal. First, need to click anywhere in the on the desktop, right click, then go to open terminal. Then once the terminal is open, go to SDE space hyphen no open caps G. And once you click on enter, this kind of window you will get. Right? This is the empty pane of this SDE. This is how it looks like. There are several options at the top. The rotation of the axis you can mark from here. You can check from here. This time, at the present moment, X is downwards, Y is left, right, and Z is into in out, into the plane, outside of the plane. Right? Here is the list of materials that are available. If you can see, there are other options also. This select option, then zoom in, zoom out, then click, then pan. Pan is ultimately you will orbit your device. Then you can align your device into multiple frames like XY frame, YZ frame, ZX frame, isometric projection frame. Right? So these are the options provided. So as I told you, once you start your device, you must have the coordinates with you. So I have my coordinates with me for this demonstration purpose. So I'll be taking reference of this example and start drawing these coordinates into that SDE. Right? So the very first option that you need to take care here once you enter into this SDE is you go to this draw part. Is it visible? Is it visible? Nothing can be done here right now. But that can't be. Yeah. That is not ultimately the geometry will be enlarged, right? Option and we speak. So the very first option that you need to go when you open that SDE is go to that draw part and untick this auto region naming. Right? Once you create a particular layer, you obviously want to name it according to you, not automatically. That's why I have unticked this option. Then the second thing is just click on this exact coordinate mode. It will turn on that exact coordinate mode. You don't want to drag your geometry. You don't want to take general measurement of the geometry. You want to be precise with your geometry. That's why I have taken this exact coordinate model, right? So these are the first two options that you need to take care once you start with SDE, right? Also, there is one thing: if you don't get the scheme command prompt opened when you start SDE, no need to worry. Just click on this part, and the very first option you will find out scheme command. It is unticked right now. That's why you will not be able to see that command, that scheme command prompt. Right? Once you click on this scheme command prompt, you will get this command prompt. Right? This is how it looks like, empty. Right? So till now I have done a single step, which is setting up the auto region naming of, right? So that step got printed here automatically. So I'm closing it for now. Now we are taking an example of this MOSFET. So let's try to draw this. So I have taken a material as silicon first, and now we are creating a 3D geometry. So I'm clicking on this cuboid icon. If you are not able to see, I'm speaking, just hear it properly. I have clicked on this cuboid option, right? Now I can drag anywhere because I don't need to worry about the dimensions since I have turned on that exact coordinate mode. So it will ultimately be asking me the coordinates that I need to create. It is asking for the cuboid coordinates, right? I was talking about these coordinates. When you start creating a geometry in your SDE, you first have that pen paper drawing by yourself, right? And you should have that coordinates. Otherwise, you will be stuck at each and every step. So I have those coordinates with me. I'm just entering it for you. Zero and then y2 minus, then y2, and then right. Now once I enter all these coordinates, I have just pressed enter, and now it is asking for the region name because I have unticked that auto region renaming off. That's why it is asking me to name this region, right? So I want to name it as subsilicon, substrate of silicon, and enter. You can see a keyword created here. Just press escape to remove that already selected command. And first, I will click on this isometric view so that you can take a 30 angle view. This is how we draw a cuboid in this Centauros structure device. Centauros structure editor, right? So once I have clicked on this Centauros structure editor and I have drawn a cuboid, now we can move further to other layers. Before moving to the other layer, first we'll see that scheme command printed for this particular step, right? So this one is the command that is responsible for this particular step, right? As I'm moving forward, the steps are getting already automatically printed in terms of scheme language, right? This scheme language becomes important when we complete a project and we want to save this particular project in terms of code, right? So we just copy that whole command that we automatically printed and save it as a separate file, right? Ultimately, we can get again this particular project by using those scheme commands. Just copy and paste here, and that geometry will be drawn again. That also I will show you. So moving on to the next step is creating a right trench of oxide layer. So I'm selecting a silicon dioxide material, and again we are going with the cuboid. I've clicked anywhere, it will ask for the coordinates to enter, and now I'm entering the coordinates. So minus 0.2 minus minus 0.28 and then 0 then 0.2 then minus 0.1 and then minus 0.2. Entering these coordinates, I will just press enter and it will ask for the region name. I'm naming it as French oxide for the right part and enter. You can see this cuboid get embedded inside this silicon block, right? This happened because of this option, that overlap behavior. When you start your SDE, by default it is in new replace old mode, right? New replace old, what does that mean? It means that if a layer is overlapped on the older layer, then the newer layer will prevail, right? So it is by default. That's why I haven't ticked on this particular new replace code, and this worked already, right? So since I have created a cuboid, but from here it doesn't look like a cuboid, but it is a cuboid because it is embedded inside that silicon block, right? And here that feature called new replace code. So we'll move forward. Before moving forward, we'll take a look at the scheme command. The command got printed. Okay, then we are moving to the next step. The next step is also same. We'll do the same step for the trench oxide left side. I'll next okay. That was just for checking, right? So now I have created a trench oxide for the left part. The similar way I have created for the right part. Right? Now we'll see the scheme command got printed. Yes, the scheme command got printed. We'll move to the next part is we'll draw a side on the gate layer. To do that again we'll do the same step. It will ask for the coordinates and then minus 0.15, minus 0.2, 0 and 0.15. I have named it as gate oxide. Done. Let me check if the command got printed or not. Yes, the command got printed. Now once we are done with this, And now since we are adding poly this time, so we need to select polysilicon from the material list. We have selected this polysilicon from this list, right? And now I'll do the same thing. I'll create a cuboid. It will ask for the coordinate. I'll enter the coordinate and it will make a cuboid of polysilicon material. This time minus 0.103. All the dimensions are by default in micrometer. Minus 0.103, then 0, and then 0.103, then 0.2, and then 0.1. I'll enter and it will ask for the region name. So I name it as polydioxide 1 and enter. This I have created a gate of poly material, right? I'll do the same step for polydioxide layer second. Minus 0.15 and then minus 0.103, then 0, and then 0.15, then 0.2, then 0.005. Once I click on this enter, it will ask for the region name. I will name it as polydioxide 2. Done. This side is these edges, short edges. Right? So gate is done now. We can skip this nitride spacer part that they have given here. But ultimately we check out the result which will contain that nitride, right? Because we will see the already simulated result. Now the next step is we'll define the context. To define the context, we'll go to the context and the first option is context set, right? So what kind of context we are going to add in our geometry? So that we'll see here. The first thing that we have is gate. Here is the option of edge color. Edge color has three options which stands in Boolean form 0, 0, 0, 0, 0, 1, 1, 0, 0. Accordingly, you can change the color, right? So it is in pattern of RGB, red, green, and blue combination, right? It is just to differentiate the color marking of different contacts and different color, right? So you can do anything. Thickness we can keep it same and just click on set. Once you click on set, that means this name is registered with the geometry, right? Not the position, but now the tool knows that there is one contact whose name is here, right? Where it is placed, it is not yet defined. The next thing is drain and set, then source, SOU, source, and change color of source, set, and then we have a substrate, right? Once you click on substrate, set. Once we have set all these contacts, right? We'll click one by one on each contact and we'll activate them at the present moment, right? So all four contacts I have been activated right now. I'm closing this dialog box and we'll check the steam command whether they are getting printed or not. Yes, they are getting printed. All the four steps are written here. The contact that I have defined is gate, drain, source, and substrate. Right? Let's close this and move forward. Now the faces that we have already named and created, we can add the contacts into that faces. The faces that are not yet defined or the contacts that are not yet defined, we can't add those contacts here, right? So we have already defined this gate and sub-silicon substrate basically. So we can start adding the contacts at these places. But the drains and the sources are not yet defined. So first we need to define those drain and source area. Then ultimately we will be adding that contact on those drain and sources, right? So we are setting the contact at the existing faces. To do that, first what we need to do is from this part, you can see there are multiple options that if you want to select something, what options you have. You can select the body, you can select the face, you can select the edge, you can select the vertex, and the last option is reference evaluation window. You might not be seeing here. It is written REF/EVAL, reference evaluation window. That I will discuss what it is. So now we need to add the contact at the faces. That's why I am selecting the face. So the select face option is now being enabled, and now I am click on this select option, select cursor, and now I'll select these faces, and accordingly I'll enter add the contact. I have just right click here, and I got that option contact, right? And go to this gate. Since it is a gate, I am clicking on this gate, and I have added the contact here, right? Now I will turn this device upside down so that I can add the contact at the substrate. Again, we will do the same thing. Face, which is being already selected. If you have selected, it is already been selected, right? So click on this select, right click here, contacts and substrate. The two contacts have been added here. The first one was gate, and the second one was substrate, right? Now we will proceed with the drain and source. Since we haven't created the area dedicated for the drain and the source, we can't add the contact at this present moment, right? Now to do that, what we need to do is we will create the region for drain and source separately. So if you want to drop the previous selected option, you can just press escape, right? Now we will select the metal from the material. Why I am selecting material, I will define you a bit later. I have selected this metal, and now I am creating a cuboid. Point 0.17 done, and I am naming it as source. Okay, so you won't be able to see any changes, but those changes have actually happened because I have turned this device upside down. Here you can see. So I have created a cuboid of metal and patched it at this particular area. Why I have done this, I'll tell you after a short minute. Again, I'll do the same thing. I'll select the cuboid. Material is metal. This way, minus 0.25, minus 0.1, then 0, then minus 0.17, then 0.1, and then 0.05, and okay. It is asking for the region name. I am naming it as DRS drain and okay. Done. So ultimately we are having two metal blocks here, which are nothing, just marking up the area dedicated for drain and source. How? Now what we do, we had to select a complete metal block because we are ultimately, our objective is ultimately to mark the area for drain and source. So we are trying this method. What we are doing actually is we have created two blocks of metal patched with this silicon block. Now we delete these two metal boxes in such a way that they will leave the imprint on this particular silicon block. In this way, we will get two areas marked with drain and source. Right? So this is how we are using this method to mark those two areas. So now we want to delete the complete metal area. So ultimately we don't need to select the space this time. Ultimately we have to select the body right now. Okay, so I have clicked on this particular option, select body. Now I am able to select the complete body by using this select option. So first take the select cursor, click on this particular metal block. Now it has selected block. Earlier it has selected only face. The reason was this option. From there, here I have selected select face that time, and this time it is select body. That's why it is selecting body now. Right? Using the control key, I can select both at the same time. Now I click on this right click and delete, and again right click and delete. Now we again check if the scheme command got printed or not. Right? In this way, it has created two regions named with this drain source. These are the two imprints that those metals have left. This one and this one. This one drain, this one is source. Now we got these two areas marked with the name drain and source. So now we are able to add particular contact to these areas. Right? So now we again proceed with that contact adding procedure. To add the contact, again we need to remove this select body and change it to select face, because contact is added on a face, not on a body. So we are selecting this select face, and from this select option, I'll be able to select this particular area. I'll right click and again go to contact and marking it as drain. Again we will do the same step. Mark this area, right click, contact, and so. Right? So now our contact setting is done at all the four contacts: gate, substrate, drain, and source. Since we have done with these steps, we can just take a look at that scheme command whether these are got printed or not. So all the steps that we have done till now got printed on this scheme command prompt. I'm closing it for now. You will not be able to see that commands. So the next step is we'll start doping into it. So there are two kind of doping. I'll show you both the ways of doping that particular device. Right. So first doping is constant doping. Right. If you want to keep the doping uniform throughout the device, right, then you have to select this constant doping option. You can go to this device option, and here you will find out that constant profile placement. Right. First you need to name here this method. So I am naming it as place constant doping dot bulb. Right. Now you can find out here three options are available here, which says that placement type could be of three varieties. The first option is reference evaluation window. The second option is region. Then the third option is material. It is simple as, like, if you want to add the doping into a particular region, right, into a complete region, you have named a particular region and you want to add that doping into particular region, you can easily go from this particular option. Just click on this region part, and the slide list will show you how many regions you have already created, and from there you can just click on that region part wherever you want to second thing is material. If you want to add doping into a particular material kind of thing, so you can go through that material list. Now comes the third option, reference evaluation window. Now if both the options doesn't go, region and material both fails. You have some specific dimensions, specific block, a specific area that you have marked, that I want to add the constant profile placement into only this much area, right? That doesn't match the condition of region, that doesn't match the condition of material. Now this way you have to first create a reference evaluation window, a short window, mask kind of thing. So just to mark that this area I want to know, right? To create that, you need to create a reference evaluation window, right? That we will see in case of analytical profile placement. So I am not doing this in this particular step. So we'll go through the region this time, and these are the regions that I have defined. You can find out those regions by their name here, right? So I have entered into the region, and now I will click on sub-silicon, right? Once I click on this sub-silicon, it has selected this particular material ready for the doping. Now I need to just change the name here. You can change here name whatever you want. I'm naming it as constant dot y, right? I need to add boron kind of doping strength, right? According to this concentration, I can add whatever the strength I want. So I'm adding 1E17 here, right? And once you click on this add placement, your constant doping will be successful into that particular region, right? Subsilicon. So I am clicking on this add placement, and now this doping has been done. I'll repeat the same step for poly also. So I need to change the name here. I'm naming this time as constant poly. And from this region mask, I'm selecting this polydioxide part, and from here I will add arsenic kind of doping here, and that doping will be of 10 to the power 20. And now I will click on this add placement and done. Right? Done. You can see whether it is done or not by using that scheme command. Right? Once you click on the scheme command, if there is some error, it will get printed. Otherwise, you can see the success of this command. Right? Now we'll see how this analytical profile placement works. If you want to add different kind of doping in different kind of region or different with related to depth or motion kind of changes you want to make, then you can also go to just devices, analytical profile placement. Once you click on this analytical profile placement, you will find out these option, file, these pop up, and now I am naming it as place AP dot source. And since we haven't created a particular depth, a particular window for this particular source till now, so I am using that reference evaluation window type option here, right? If you have already defined separately reference evaluation window, then you will be able to directly slide this list, and you will have got that name of that reference evaluation window in that list. Since we haven't created a reference evaluation window before this step, so I am right now creating this reference evaluation window. To do that, you need to select this option. Take this option, define reference evaluation window, and directly create a window here for source 0.30 and minus 0.25 to 0. since I am selecting a reference evaluation window, just like a mark of a particular area, that which zone needs to be domed, right? That's why it is in rectangular form, basically 2D. The mask is in 2D right here, because we don't want to angle a proper device into it. That's why we are using 2D here. That's why the Z parameter is 0. Z1 is 0 and Z2 is 0. Point 0.15. Need to name here as Gaussian for source. The profile type I have selected here is Gaussian type. There are 3-4 options here. Gaussian type error function you can select and multi profile. So I am selecting Gaussian type here, right? And adding arsenic content here, right? And now here you need to add the peak concentration that I am adding is 10 to the power 90. The peak position I'll keep it 0 and the junction should come at 1E 70, that is 10 to the power 70, and with a depth of 0.1 micrometer. Keeping everything same, just adding placement. Add placement and it is done. I'll do the same step on the train also, just changing the name and the coordinates. Minus 0.15, minus 0.25, 0, and then minus 0.30, 0.25, and then once you click on this define, it will ask for reference evaluation window name. I'm naming it as cost.read. Rest of the things I'll keep same. No need to enter it again and add placement. Right? Done. So done till this step, we'll move forward to add the meshing into it, right? And then we'll simulate this particular device. So we are adding, in order to add a particular mesh, again the same thing, if you want to add a constant mesh, then you need to just go to this mesh part and directly go to this mesh part, and here you need to define a reference evaluation window. In that window, already the uniform mesh will be created. Right? If you don't want a uniform kind of mesh, then you need to go to refine placement, multi-box placement. Right? In there you will define multiple boxes and multiple density of grids that you will be adding. Right? So I am going to this mesh, and then I am going to define a reference evaluation window. This time it will be cuboid, because meshing is into the device, not just over the device. Reference evaluation global, okay, and then minus 0.252, minus 0.2, then minus 0.5, then minus 0.25, then 0.2, and then okay. It has added into this particular zone, right? You can see this much area. This much area it has selected for constant topic profile, right? So I'm not going into deeper into this part. Let's close this. So I am not adding that multiple meshing into it, right? So let's just simulate it and look at the scheme command. What scheme command is. Now these are the scheme commands that are got printed for each and every step. In order to save these steps, what you need to do is just Control A to select all, and from here just copy and make a file and paste it there, just like you do in text editor, right? So I have already copied these commands. I'll reopen from there. Ultimately, when you create the device, just go through that file part and file save model. Once you click on the save model, it will create .set geometry, .set extension file, and that will be saved in SPTV, right? Since I have done all these steps, so we'll directly go to those steps. I am not saving this particular model, right? As I told you, if you want to reopen your model that you have created, you can do that from scheme geometry also, right? So if you have saved the command from scheme, then just go to those commands, pick up those commands, copy and paste it here. I have already saved these commands, so Control A and then copy, close this and paste it and this particular model, particular plane, right? So I am pasting it here, and as you can see, the geometry is automatically getting printed. Step by step it is getting created automatically, because whatever I have done, I have saved in terms of scheme command, and those scheme commands I have printed here, copy paste here. That's why it is creating geometry, right? Once it will be done, you will be able to see those commands printed. Yes, it got printed, right? Once the matching is successful, you will find out the last thing. Here it is written when it's successful, right? Once the matching is successful, everything is done. It is ready to provide the result, and you will click on this mesh, and last option is build mesh. Once you click on this build mesh, it will auto call as visual, and you will find out the result. This is how the geometry looks like that we have created right now. This is the result of it, right? If you want to see the meshing structure, the meshing grids, what kind of meshing we have added, so you can just make it enable from this option, right? If you want to zoom it, you can zoom it from here. This is the zoom of this, right? Zoom in, zoom out. Domain concentration is written at the side of this plane. If you want to make a section of this device, you can do that from this X plane cut, Y plane cut, and Z plane cut. I'm doing it for Y plane cut, just clicking on this part, and you can see the cross sectional view of this particular device, right? Now, if you want to see, you can just see here that the meshing is rare, or you can substrate is not actually the most important part in MOSFET. It is responsible for generating the result, right? Which one is most important part of this MOSFET is the channel. That's why at the channel part you can see that the meshing is very dense, right? The denser is the meshing, the more is the simulation time, and the more precise result you will be getting, right? But in order to get more precise result at each and every point of the device, you can't add. Actually, you can add, but it's not a good approach to add compact kind of meshing in the complete device, right? Because it will take exponential increment in the simulation time. So that's not a good strategy. The strategy says that the most important part, always add the compact meshing or the denser meshing in the part which is most important and most reliable part of the device for the result, in terms of result, right? Otherwise, add the rare kind of meshing in order to save your time. So that's the example what we can see here. Denser meshing at this channel part, drain source part, and rare meshing, rare meshing at the bottom part of the sub-silicon part, right? So I'm closing this for now. You can actually see the material wise sections also. If you want to just see the boron part where boron is added, you can just see here where arsenic added, arsenic you can see. So this way you can see multiple things from SD that are being generated from SD. I'm closing it for now. So the SD part is done. Now I am opening the CentOS workbench whose command is SWB. In terminals, just type SWB and you will get to open this CentOS workbench. With the use of this CentOS workbench, we will be adding two tools into it, which is as process and as device. That's how we will learn about the CentOS process and CentOS device.
Apart from MOSFET, what are different kinds of devices? Like list of devices that can be simulated.
Here,
Apart from MOSFET.
there are so many. I have included that in application library. All those steps of the electronic network, organic devices. Organic devices actually not referring to because it doesn't allow you that much extent till research because it's newly added. The rest of the things that are included in the application
You see the library.
from here itself you can use. These are the list of examples and libraries given in SW. Right? So let me read it for you. Advanced transport, that analog, backend, bipolar, CMOS, FinFET, and in getting started, there are basic examples. Then heterostructure, memory, optoelectronic devices, power devices, reliability sensors, solar, and different aggregates. Right? So these are the models, these are the application libraries that you can use in particular this. So the first thing that we look in this is as process, how it works, and the basic concept of the test process. As process is ultimately very critical and very complex thing. So just to know the fundamental, we'll just go through the flow of that CentOS process and test device. Right? So to just understand the CentOS process, we'll take an example from getting started. And from getting started, all these change this. Actually, these examples are already made in terms, if you are a beginner, then you should start from these. Right? So in getting started, I am going into S process, and here there are two options. One DGS, you can try and two DGS. So I am clicking on this two DGS, and once you click on this, right, these yellow marks you will not be able to see. You will see the white part, right? Since simulation takes time, so I have already simulated these. That's why it looks yellow. Yellow means done. Red means fail, right? And green means in a queue or ready or pending. This is stage, right? So since it is yellow, that means I have already simulated it, right? So this is an example that is being created by Synopsys itself. It is for demonstration purpose. So now I am right clicking on this particular S process. And if you want to see the command file of this S process, what commands they have written, how they have simulated, and what it should give. If you want to analyze these kind of things, then you need to go edit input and command. Once you click on this command, the commands will get opened in front of you, right? So I have just copy paste this command in text format so that I can make it true for you. So I made a PDF of these commands. Now you can see that in case of S process, the hierarchical steps looks different than the SDE. Right? In case of SDE, we were first constructing the geometry of the device, then adding the dopents, then declaring these contacts, then we are adding the mesh into it, then we are simulating. But as process is something different. That make it complex. The procedure and the hierarchical steps that are being defined in as processes almost reverse of that SDE. Here at the starting you are looking at this initial grid, they have already defined the initial grid at the starting of the device, right? So that's the format and that's the syntax, how to define a particular grid. So these are the keywords that you are looking here. That the line at x-axis with the location of 0 along with the spacing of 1 nanometer named as that particular layer or that particular point is tag means that's named as silicon top, right? And from their silicon top till the x-axis end, it is extending the grid spacing and the grid, right? So X location 50 nanometer spacing 10, then 0.5 micrometer, then spacing 50 nanometer, right? So it is as going to 0 to 10 micrometer towards 10 micrometer, it is increasing the spacing of the grid. So basically, looking at this, we can say that it is using actually the analytical profile placement concept, right? So that kind of meshing is used. Multi-box refined placement. In the Y location, this is added space 50 nanometer, and these are the different tags that it has given to it.
This machine is already done in the earlier step. Now it is repeated once again. This machine was already done in the earlier step.
But that was different one. This was different one.
This is different.
That we have created, that we have drawn now. It was just for demonstration purpose that how to draw a device. That device I have drawn, edit the mesh
In the GUI.
So that part is separate. This one is separate. This was created by Synopsys itself. So they haven't designed that as data that I did. So that was my project. These are different. Just it was for study purpose. That's why I am opening different examples. Right. Then they have defined the silicon substrate, and this is the way that defines the silicon substrate region. If you look at these, if you look at these code, it slightly looks similar like scheme commands that got printed during that SAE. As the just the difference is just of the syntax. The keyword remains the same. Here also region, then the name of the region, then what we are naming it, then what kind of step we are adding, right? These kind of things, they are the options are, right? And here also they are mentioning these steps. That the region will be the keyword, and the material that you are using, the name you are giving to from top to bottom, the left to right. This kind of procedure they have used here, right? Now they are initializing the simulation with the initial concentration of this, then phosphorus, then they have now they what makes it different is along with the geometrical construction, they are also adding the processes that are involved in fabrication of that particular device, right? So they have started adding these boronucleate implant into this particular device, right? So they have done this in three steps basically. The first step is with a higher energy, just to create a P-well. Then in the second step, they have tried to create a retrograde boron implant just to prevent that punch through, right? And in the third step, they have tried to just modulate or control that needle.
I mean, the earlier thing that you spoke was independent of this. Sorry? The earlier thing that you spoke is independent of this.
Right. Independent.
Independent.
It's like this is example that was being created by someone. That example was designed by me, and I made it, right? So I designed it and matched it with these
So
other
it
sides.
did not work on the GUI interface also.
Although we are constructing the same device. Right? It's like I am constructing my boyfriend, and you are constructing your.
That is what I'm saying. You did not use the GUI interface all the time.
Right? As the uses GUI. Actually, it's an optional. If you don't want GUI, you need to do this way. Either you can go with this. If you know scheme command language, then directly type in the scheme command, paste it there, and it will automatically calculate with the language. So these are the steps that we need to follow as process to provide different processes to add different processes into this particular device. Diffusion temperature they have added. Now they are saving this structure. Wherever you see at the rate node at the rate, that means here the compiler, when the compiler will run, it will add 1, 2, 3, that is node number, right? Let me show you that node number. These each blocks contains a node number, right? So these node number will be added in place of this node at the rate node by the compiler, so that you can generate the file. Ultimately, at the rate node at the rate makes it generate. Just like n at the rate node at the rate means once the compiler will start generating it, there may be multiple iterations, right? So it will take the name n1, n2, n3. So ultimately this node will be replaced by the node number there, right? That's how you will get to know that which file is which one and which file is which one, right? Then gate oxide process they have done with the diffusion layer, diffusion temperature. Then again they are saving the structure with n at the rate n. This time they are producing that, naming it as n MOS for the gate oxide. So what they are doing is, as they are moving with the steps and the processes, they are at the time of simulation, they are generating different files and the different steps, so that they may get information about the device, that how it is getting processed, right? So they have generated the output after one process only, after two process separate, after three process separate, after completion of the device separate. So that's how they will get multiple results, and you will be able to look at the device along with the process. That this is how it looks when it is completed 10%. This is how it looks when it is completed 30%. Similarly, multiple files moving it. what it is doing by using this, right? So this time n was 4 multiple times, right? N was 5. So after each process that it is being added, it is generating an output just to visualize the process changes on a particular device, right? So once you will take a reference of that manual, you will be able to understand more depth of this across process. Here in each and every step, it is totally dedicated to the processes that are involved during the foundry fabrication. Right? What are the fabrication processes? You must have a good knowledge of this. That's why it is barely used. Most of the time, ST is used and then directly we go to ST because having that foundry knowledge is a big thing. Right? So TLX is the extension of the file that mention that if there is a not we can say extension. It is before the extension. Before the extension, if you find TLX written, that means this file, that particular file, whatever it could be, the TDF file it may be, that log file it may be, but if it has TLX before that extension, that means this file is generated by CentOS process, right? So this is how you can identify a particular file. Right? So this was that S process. Now we'll look at that S device also. Templates. We go into templates and we'll select the elements from here. Right? Here you will see that they have added the S process along with the S device also, and they have also added S visual just to visualize what is the input and output. Now once you click on this S device, you will find this file. There are multiple sections that you need to define when you are creating a command file of S device. The first section that comes is the file section. File section, as the name suggests, is the collection of all the files that you are providing as an input and that you are expecting as an output. The name only, right? The name only of that plot, the output, and the name of a particular file that you are giving it as an input. All these collection and the names of those files need to be mentioned in file section of S device. Right? So this was the first section of command of device. Then the second section comes electron section, where initial biasing of all the contacts and all the electrodes that you have mentioned in your device, along with those initial settings, initialized, defined. Right? Then comes the physics section, the most important section on which this complete S device rely is the physics section. Now, as you can see here, there are two physics sections. The first section, which is defined as physics and directly Fermi and then hyperdynamic models are added into it. So that says if that above the first one physics section is basically the section which defines the physics part or the models that are defined in this particular part are implemented in global. Global means during the complete procedure of the device. Right? It is not specific to region, it is not specific to material, it is not specific to anything. If you add some model into this particular column of physics, that means you are declaring that this model will be globally included in this particular part. Right? Then second comes the physics part again, which is a local part, which is dependent on some region or some material. Let's say if you want to add some physics in a particular material only, then this physics option is applicable to you. Just like here, they have added a material silicon. This physics part is only applicable wherever the device has silicon, right? So E quantum potential model, mobility model, E normal model, these kind of models will only be applicable on the silicon material in this device, right? So this is the physics section which is locally available, and the earlier one was globally available. Then comes the plot section. Plot section basically means according to the model and according to the inputs that you have provided to the S device, what outputs do you expect? What parameters of the output do you expect that your model can generate in this device? Those things you need to mention in plot. So basically what happens is if you don't know the capability of producing what parameters as an output by your model, then what is the best strategy? You just write all the parameters, all the outputs that you can think in plot section. Whatever your model is able to deliver will be delivered, otherwise it will be empty, there will be no error. Right? That's why everything is written here. E density, H density, total current, then temperature of E temperature, hole temperature, normal temperature, potential scale chart, everything that you can think is written here, right? Doping dependence model is must, but mechanical stress model is by choice, right? So although they have added these stress outputs of stress models, whether they have included stress model or not, but they are expecting that this output may come. Okay, so if that model has the capability to produce that stress level output, it will produce. Otherwise, it will be blank. Then comes the math section. Ultimately, whatever we have defined models need formulas, calculation, classic physics is applicable there, classic mathematics is applicable there, right? To solve those problems, ultimately we had to apply some mathematics there, right? So extrapolate and then derivative and then error control methods, digits. Digits have their own significance. There's a formula, some 10 to the power, some minus digit. Ultimately, if the differentiation dx by x comes less than 10 to the power minus of digit, then it will stop the iteration. Ultimately, this is the reference of that digit. Right? Each word has their own significance, own reference. That to know depth of each and every word or line, we need to actually take reference of that model file and also this manual. Right? So the number of iterations here written as 25. It can maximum be 100 available. 100 is the maximum limit and 1 is the minimum limit. Right? That depends on your research or your project. How uh, how easily or how quickly you expect your iteration, your project to get converged. Right? So accordingly, you need to increase or decrease the iterations, the number of iterations. The more the number of iterations, the more will be the simulation time. Right? Then comes the number of threads. The number of threads mentioned here is 4. It is directly related to the number of cores of the processor that you have. Octa-core, dual core, or quad core, whatever you have. How many processors do you want to dedicate to start simulating this particular device? Right? So if you want to make it faster, then you need to increase the number of threads. But ultimately, your cores will get dedicated to that. Right. Then comes the solve section. Solve section is the only section in which the hierarchy of each and every step matters a lot. Right? Which one is written at first, which one is written at third, which one is written at fifth matters a lot in solve section. Right? Rest of the sections, any line can be up and down, but in case of solve section, every line should be in a particular hierarchy. Right? So this is how they have created an initial gas, and then Now they are providing the initial, the final ramp. Basically, they are providing the signal, input signal, so that they can plot a graph ultimately as an output, right? Because ultimately our motive is to get the IDV curve, right? So this is the VT suite. Accordingly, the VT they have ramped, right? So ultimately, they are providing the input signals to the device, and accordingly, it will produce the IDVG curve for us. So now that device is also over. So once we have understood this, I have already simulated this. Now we can click on this node number 1 and we'll click on this I option. I option is actually the icon of S user, right? So once we have selected this list completely, which is already simulated, that side will quickly open, otherwise it will start simulating, right? Because I have already simulated, this is in yellow. That's why it will not take time, it will directly produce the result, show you the result. Otherwise it will take dependent time, right? 1 or 2 or 3 or whatever. So I am selecting this one node and I am clicking on this I option, which is for SD. Now here we are provided with three options. You can select a particular file. There are multiple outputs generated. If you want to see a particular file, you can just select that particular file from the very first option, which is select file. Then comes the second option, which is select by type. Select by type means the type or the extension of output. Let's say .tdr file you want to see, but the .tdr files are four or five files that contain .tdr. If you want to see all the TDR files together, then you can go to the select by file type, right? Then the third option is visualize all file. All file means whatever is generated, just open it. So we'll take a look at all file first. Now if you look at these output that contains underscore FPS. FPS, wherever you see FPS, that means it is related to S process, right? And if there is PLX, that is also related to S process, right? So these looks like a line, but these are actually the result of S process stepwise. After two processes, one output is generated after four steps. Four processes, one output is generated. So there will be development of device shown in these pictures, right? So if you want to zoom any one of it, you can just click on this and then zoom, make it bigger. Like this, it looks like. You can't see it right now, so we'll make a. Now you can look at that step. Half of the geometry they have created right here, right? So this was the second file I have opened, right? Now if we look at the third file, some more process will have been added into this output, right? So this was the ultimate result of that node at the rate node at node at the rate node, node at the rate node, and most one, and most two, and most three. After two steps, one produced. After three steps, other produced. After four steps, other produced. So that's how we can easily visualize that this process made this change in my device. These processes made this much change in my device. Yeah? So we can easily analyze, right?
What is this X and Y axis? This is X and Y axis represents X and Y axis represents.
No, I mean it's just a length in case of this because x and y axes are for geometrical structure.
Geometrical structure.
What is this parameter being displayed?
Sorry.
What is that parameter being displayed?
Doping concentration or what?
Doping concentration. What you were saying, sir? Material limit.
For boron, because 1 is getting to 70, 1 is 70.
Concentration is big, it's big.
Right, right. But what 1 is to 10 to the power 17? That I have it.
For boron and for arsenic, same.
Now this file I have opened, second one. Now we will look at the third file.
Substrate to activity substrate cover. That one is cover.
These are the changes in the third file. After some other processes, then you can take a look at the other part. After some processes, this generated, right? Now, if you want to analyze after which process we generated, that you must already know, because in that case you would have written that code. Just because it is an example, we are not actually able to get that after which process which result came. Actually, we can, but it's a complicated process. We'll go to that code and we'll then analyze what process it has done. Then we'll take a look at the node. Then we'll come to this part, and from here we'll get the node number. Then we'll go to that output part. We'll analyze that whether the node number is 1, 2, or 3. If that 1, 2, or 3, then accordingly we go back to the code and we'll look at which node number is generated after which step. Right? Ultimately, you need to cross verify. So this was another file, and that was another file. So this is how the process is going on. Right? Right. Now comes the plot part. The plot part seems to be empty here because it contains plot information, but till now you haven't defined the x-axis and y-axis. So it's up to you what you define on x-axis, what you want on y-axis. That's why it is blank right now. So we expect IDVG curve here, right? So we expect IDVG curve here. So we'll just click on this plot and we'll find out these options. You see these options? Okay. So it is here. It is showing the multiple files that are generated, right? Node 2 file is generated. Node 2 file is generated. Node 4 file is generated, right? So we have selected node 2 part, identity curve for simulation of node 2 part, since it has added two Centaurus device. So two files are separately generated. Okay. So we are looking at for the node 2. Now there are so many options at this part, right? So since we expect IDVG curve, so we are taking the outer voltage at the gate terminal to the x-axis. What does that mean? At x-axis we'll have the voltage Vg, right? And now we'll have the ID, that is total current of drain, at the left y-axis, and this becomes the curve. We get that IDVG curve. You can take a look at this curve, right? From here, this option you can just name the plot whatever you want. You can name it, and the background option, foreground option, the frame, these kind of just options you will get from this plot property, right? From this plot property, I have enabled the grid so that we can mark up the vertices and the point by point changes into that graph, right? So as from here you can.
No, ideally.
Right? It is going to 0, 0, 0, 0, 0, and then after the threshold, it starts going up.
Threshold. Then IDVD.
Sorry.
IDVD.
IDVT, you need to make changes into code to get IDVT. This code code is actually written for delivering IDP.
IDPG.
Right. You need to make changes in that solved part. VG sweep and VD sweep.
Yeah.
You need to make changes accordingly, and then it will produce that IDP. Right. One more thing that you can do here is once all files get ready to open up, you can do one more thing is if you want to analyze complete property of all the processes that have been taken place in these. So you can just select Control A. Once it will press Control A, it will select all the frames here, right? And accordingly, you can just go to this part which says link. So all these output frames will get linked together, right? So in that way, you don't need to go to one, then two, then three, then four. All will combine and will become a single file. And that single file will have the property of first one, second one, third one, fourth one, fifth one. So that's the benefit of using this linked kind of thing, right? So once we click on this link, this node should not be linked. There was some shortcut to show that device. Function F9 was there. I just forgot that option. Once you click on that link, there is some key that you need to press to get that device. Right? At that moment, I just forgot that key. But no issue. That from these XYZ planes, you can just take out that sectional view of these, right? And you will find out the AEC. The cut line, this is the cut line graph produced here. Maybe it can produce that also Venn diagram. Yeah, it can produce that Venn diagram, right? So all these things that I have been showing you is dependent on your model. If your model has that capability that it can produce these kind of results, then only you will be able to see. Otherwise, it will show error once you will open. No error in simulation, but once you will open, it will say that there is nothing in this file, right? So this file is created for demonstration purpose by Synosis, so it has all these features. So I will be able to show you all these, right? So ultimately, you got these options and how to use this, and this demonstration was for a purpose that you need to know the flow of using this particular tool, right? At the technical end, obviously, every person needs to work accordingly. You can take X, Y, and Z log scales also. Once you produce that IPVG curve, you can take reference of this log X, log Y, and log Z, right, for your calculation. Right? Once you click on this one, you will go to this visualize, and from the select file also. Once you click on the select file, you will see that the files that have been generated in total, right? So to know about these files, to open these files, you must know that which file is responsible for which thing, right? So to have that knowledge, you must know that section. .plt stands for plot part. So if you want to take a look at the graph directly, you don't want to see the complete rhetoric part or complete symmetrical part. You directly want to see the curve, right? So you can go to that .plt part. Now the last thing that is important here is if let's suppose in CentOS process you are going through multiple processes, but you don't want to define a particular temperature at that particular moment when you are coding. You don't want a particular process to happen at temperature 1000. You want to make some changes. You want to analyze some changes in your device according to temperature, right? So in that case, what you will do is you will make temperature as variable, not a constant, right? Ultimately, in code, what you have to do is you need to mention in line that temperature is 1000. In neckline, that temperature is 800. In neckline, temperature is 500, right? Once you will get the output, if you are not satisfied with it, if you want to do some other changes, so you will go to that code, make changes in temperature again and again simulate, then again it will produce some result, again it will take that much time, so it will become complicated. So it's better that you will make that particular parameter as variable that you want to change, keep on changing, right? Let's suppose you want to make changes in temperature. Once you see the output, you again want to see output for different temperature this time, right? So the strategy is make that temperature as parameter or variable, right? So now the temperature will become at the rate temperature at the rate, and this way it will become a parameter. If you start simulating the parameter, if you start simulating the code without defining temperature this time, it will produce an error that you haven't defined the temperature. How can I start? Right? So in that case, if you will make it parameter, then you get one more benefit is that click or right click here, edit inputs, and here you get the option of parameters. So parameters, once you click on parameter, all the parameters that you have defined in the code, you will get those options, right? So if you have defined temperature as a parameter, you will get, once you click on this parameter, you will get different values you can enter for that temperature, right? So now the complete code running itself take temperature number one that you have given. Let's suppose we have given simulated at 1000, 800, 600, then 500. So now it will run, take 1000, produce reading, run, then take 800 and produce reading. So you don't need to go and change manually again and again into that code. You can do directly from here. Although the difference is slight bit, but at least your handling and the user experience becomes good, right? So you can do that from this parameter. Include materials means ultimately that material DB case. If you have created a material, you can include a material from here. But for that, you need to include that material in the file section also, and you need to keep that material into that working directory also, right? And you need to keep that material in the material DB also, right? So if you don't have, since no one knows the exact and all the parameters of a particular material, so it is always suggestible that you just choose a material which is closest to your material from the material DB portal. Pick that, make a copy, keep aside that original one, and now the copied one, make changes in that copied one, make some changes so that if something gets wrong, you have the original one, right? Make it changes, give it your name, your material name, put it in material DB with your name again, put it in your working directory, and put that name in file section also when you start coding into CentOS device, right? This way, your material will get added into S device. Now, once you start using that S devices, you start simulating, then you will immediately get result, error, whatever. So this is what the parameter was about and the material. That's it from my end.
Participants ने कहता है announcement रखना है ना, all of them. GS ने
Thank you, thank you, Engineer Vyom Sharma, for your talk on